Right.
Yeah, I
Oh,
know for sure.
thank you so much. I'm just setting up the YouTube stream as well.
Yeah, yeah.
So that way is the video, whatever we record once we start, it gets directly uploaded and we don't have to download the recording and later on. So
No
it
problem.
will make it easier to distribute later on. And if somebody wants to watch, we'll
No
just
problem.
share on our page.
No
Yeah, I
problem.
know for sure.
Thank you so much. I'm just setting up the. Okay. Page.
No
Yeah, I
problem.
know for sure.
Thank you so much. I'm just setting up. Okay, it's working. Okay, I think we can start going live. And once we do, we'll wait for 3-4 minutes so that maximum people can join and then we'll
Yeah.
start the session.
Sure, sure, sure.
Hello, everyone. Thank you for joining in. We will wait for another couple of minutes and then we'll start the session. Hello, everyone. We'll get started with this session. So thank you so much on behalf of AV Reporter and XproEM. I would like to thank you all for making time for this important discussion. So in this session, we're going to talk about the current challenges with the lithium-ion battery recycling technologies. And we will also like to understand more about the proprietary technology, the solid state technology developed by XproEM that can provide us a sustainable solution going ahead for lithium ion battery recycling. So how it will work is we will have some short presentation from the leadership team at XproEM, and it will be followed by half an hour of interactive Q&A between the audience and the lithium-ion batteries and recycling experts we have on the panel. So I would like to invite Mr. Nishit Patel to start with, and he's going to be speaking on the role and importance of lithium-ion battery recycling for our battery-powered future. Nishit, over to you if you would like to share your screen.
Perfect. Thank you so much, Priyakshi, and welcome everybody. I'll just get my screen share set up and we can get going. There we go. Perfect. So I'll start off the talk today by discussing the role and importance of lithium-ion battery recycling in what's shaping up to be this battery-powered future, and welcome everybody to our talk today. So we'll set the stage by saying why and what are lithium-ion batteries. So lithium-ion batteries are predominantly used as the battery of choice in a number of different applications, ranging from consumer electronics to all types of electric vehicles. Um, the key materials that are used in battery production include graphite for the anode, as well as some key metals. So I list lithium, cobalt, and nickel that form part of the cathode active material, or also referred to as black mass. And in terms of value, um, of all the different battery components, cathode materials themselves represent over 40% of the value from a typical battery cell. Now, in terms of the market for growth for these lithium-ion batteries, the use of these in electric vehicles is expected to be the primary driver of growth. Specifically from a number of projections, by 2030, they're expected to be over 140 million of these vehicles on roads. And what that means is that once these batteries in these applications reach their end of life, this is now what requires recycling, specifically from these EVs, but also all kinds of other applications. So just speaking in the next 4 or 5 years, there's already an anticipation that there'll be over 2 million tons of spent EV lithium-ion battery packs that will require recycling. And this just in terms of a market value alone represents a value of over $10 billion. Now, before we understand, how exactly do these batteries get there, we'll talk about the current setup in terms of the life cycle of lithium-ion batteries and how we can move towards getting a truly circular economy for them. So currently you mine these raw materials that are used within the batteries production, so cathode and anode production. They end up being used in a number of these applications, and then they're disposed of. Usually that's very not done very environmentally friendly. Obviously, it's either stockpiled in a warehouse or disposed of in a landfill, like I said. So to achieve this truly circular economy, a number of different approaches could be used. We'll propose that a multifaceted approach is kind of the best way to achieve this, ranging from technology improvements that help with how batteries are used and how they can be extended, or their life can be extended. Second life application, so thinking about reusing and repurposing them, followed by recycling. And what this looks like in just a similar kind of a flow sheet is you have the same kind of setup, but after application and use, you either repurpose for second life applications. We'll see some challenges that are associated with that, and then recycle or just recycle directly and minimize that disposal, if at all, if we're looking at a truly circular economy. So on the technology improvement side of this solution, we're looking at improvements all the time in the battery related field, ranging from having a lower price for these batteries, increasing the battery pack sizes in cars and how much can fit, improving energy density. And, these three kind of tie together. On the right, you could see an example image of the Tesla battery pack and how it fits on the bottom of the car. And then also looking at improved battery design, configurations, and other systems that all in the longer run lead to also longer battery cycles and calendar life as well. When we're looking at the second life applications, you could reuse these modules, say from one EV, and use them in another if there's some issues. You could repurpose these retired batteries for stationary storage applications. Again, there's some issues associated with that, but generally speaking, you can extend the battery life if used in a secondary, less demanding storage application once the batteries don't hold as much charge, for example, as previously. Barriers to implement some second life applications include some things on the performance and reliability of these batteries compared to new battery storage. sometimes the refurbishing can be costly and time intensive. There's different battery chemistries that all require different or that offer different properties. So some of those also come into play. And then also dealing with things like proprietary battery management systems, and also just collection and handling of and transportation of these batteries, because in some places they're classified as hazardous waste. So we then come into the portion of the kind of supply chain that we talk about when we say we should recycle, and why should we recycle? Beyond the obvious environmental reasons, where they could spend batteries can be toxic, but we also get a reduction in greenhouse gas emissions when you're comparing to sourcing raw materials freshly from mining, for example. On the supply chain side, obviously, we can have recovery of these metals and minerals that reduces the demand for these key raw materials or serves as an additional source of supply. And this reduces reliance on imported materials when domestically recycled. On the social side, we get to reduce negative local impacts from mining and refining. And economically, obviously, this offers a profitable recovery of some of these key valuable materials. What are the steps used today to recycle lithium-ion batteries? Involves three broad steps, ranging from material collection and preparation to some sort of pretreatment and mechanical pretreatment. So this includes shredding and sorting to separate these materials and isolate that black mass powder that I spoke of earlier. And then we move on to material recovery, which takes two forms primarily today, either a pyrometallurgical side, which involves high temperature smelting, and a hydrometallurgical side, which involves usually leaching with some sort of acid, base, or solvent, and then recovering the materials that way. Now, some of the issues with these current technologies are that there's high operating costs. They still have environmental related costs when we look at recovering, for example, or treating toxic wastewater. And then there's also sometimes lack of raw material and production flexibility. So the industry in general, even in this recycling space, is in need of a good solution that can offer both environmental as well as economic benefits. At XproEM, and we'll talk about these a little bit more as we get through the presentations today, we go through, when talking about the pretreatment step earlier, we go through our physical separation process, which allows us to recover all components from a typical battery pack, followed by the material recovery stage, which has two technologies that we employ. One is the solid state subtractive technology that we'll talk about today, that allows us to extract these valuable species in a step-by-step way that does not use these harmful chemicals such as acids, bases, or solvents. And there's a diffusion-driven doping restoration technique, which allows us to directly recycle cathode and anode. So before we move on to the next one, I'll just reiterate, use of lithium-ion batteries, again, primarily in electric vehicles, is expected to fuel growth in this space. To create this circular economy, we'd like to have a multifaceted approach that allows us, to not only improve the technology for batteries, but then also apply them in second life applications, followed by recycling or direct recycling. And whatever this recycling solution is, it needs to have both environmental sustainability as well as robust economics. And with that, I'll happily pass on the presentation back to Priyakshi.
Hi, I just realized I was on mute. Yeah, so thank you, Nishit. I think that was a very comprehensive overview of the current lithium-ion battery, the market for it, and as well as the need for recycling the batteries. So that's very useful. Thank you for that. And with that, we will move on to the next presentation by Brett. So Brett is the co-founder at XproEM, and he will be speaking about what are the current technologies that are commonly used in lithium-ion battery recycling and what are the areas of improvement there. Over to you, Brett, if you could share your screen, please.
Yes. Hello, everyone. Just let me try to find my sharing.
You can find it on the toolbar, in the Zoom toolbar.
Yeah, just I was looking for the screen specifically. No, not this one. So give me a second. Okay, now we're good.
Okay.
Is this viewable, the screen?
Yes.
Okay. Thank you, everyone. First of all, I'd like to say it is our absolute pleasure to be here and talk about this lithium battery recycling overall. As Nishit mentioned earlier, there's a huge market with fast-growing potential in lithium battery recycling. As the recycling will become more urgent once the battery are retired from end applications, which was actually already happening right now in a lot of countries and regions. What we understand from our conversation with local players is that there are several challenges are currently faced by the industry in implementing efficient recycling. And today I would like to use this opportunity to briefly introduce some of the key issues present in the lithium battery recycling ecosystem in general. Okay, so first of all, the challenges are present in the following areas: regulatory and legal framework, which is generally marked by a lack of oversight from government agencies, and the industry standards and the guidelines for recycling operation, as well as insufficient laws and regulations and with enforcing actions in place. Secondly, collection and the transportation of lithium batteries can be a challenge from standard safety and logistics standpoint. As safety remains a key concern in handling lithium batteries. Technical challenges are also contributing to the complexity for recycling, mainly due to the negative environmental impact from existing recycling processes, as well as inadequate feedstock flexibility and the compatibility, which is making it harder to gain the economics of scale while maintaining the required high recovery rate and the purity. For this part, I'll leave much of it to Kinnor to elaborate on in his talk. Lastly, current recycling practice suffer from poor economics in general, which is also making it harder to launch new recycling project in a larger scale when the return on investment can be below the hurdle rate for a lot of investors who is interested in this business. Next couple slides, I prepare a quick summary on the general legal framework on lithium battery recycling. I see some questions in the toolbox, in the question box. And so I'll try to cover some of the largest markets. The first one, let's look at the United States. So despite the recent uprising trend in the renewable energy related project and company in the stock market since last year, the recycling of lithium battery is only strictly implemented under only 3 states in the USA. So it's New York, California, and Minnesota. And each state has its own standard and the regulations in managing and controlling spent lithium batteries, either from a reuse or recycling perspective or with disposal standpoint. So we believe as a lithium battery application become more and more widespread in the USA, particularly as the electric vehicles are starting to take more market share, there will be more states join the 3 right now to set up the proper program. Next, we can look at Canada. So Canada is a lot similar to the USA in terms of the recycling of a lithium battery are regulated at the provincial level in only 4 provinces and under the general waste recycling legislation, which within the broad category of battery rather than having a separate set of standards. So as we understand that lithium batteries are quite different from the lead acid battery or any other battery that we're using right now. So and lead acid battery are commonly used to set up the standard. So we see there's definitely area for improvement in addressing the unique features with lithium battery. And now we can talk about the EU. So the European Union has the most advanced and developed program for battery recycling in the world so far. So this is basically summarized in the EU battery directive. The EU Battery Directive is a really comprehensive guideline for outlining the regulations for handling spent batteries in Europe. Especially, it requires manufacturers of the battery to be responsible for ensuring the spent battery to be properly managed and handled. And this is the same. And this is the same thing as in Canada. It's the battery manufacturer's responsibility to properly handle the spent battery. And lastly, we can talk about China. China, basically, on the other hand, has the largest fleet of electric vehicles powered by the lithium batteries. And the need for recycling is definitely most imminent and urgent and substantial. For batteries from personal electronics, in China, the recycling is regulated under the general procedure for electronic product waste. However, due to large volume of the lithium battery used in electric vehicles, Chinese government actually has passed a guideline specifically for recycling the batteries, the lithium batteries, back in 2015, and which is followed by a series of industrial standards set forth to aid the effort in promoting and standardizing the proper lithium battery recycling practice. So in a nutshell, we can see there still quite some room for improvement with tighter regulations and particularly more enforceable measures. And the second topic we're going to talk about is for logistics and transportation. So collection has been a challenge for sure in many countries and regions for the following reason. Number one, lack of a clear pricing mechanism, which hinders the smooth transaction between the end users and the collectors. Number two, there's actually a shortage of designated collectors or collecting sites. And thirdly, there's insufficient battery life information tracking system. Basically, would have been helpful for the end users to monitor the condition of their batteries, and for recyclers to proactively source the near retirement battery when reaching out. So adding to the difficulty, transportation and the storage of spent batteries also require specifically designed vehicles and the warehouse in order to address the safety issues for handling the battery before discharging. So far, on-site discharging has been a popular idea around, which reduces the challenges in moving and storing the battery pack. However, the current technology, as we understand, has not been available to support this. Another key factor to consider is the cost when transporting the battery packs around. Because a lot of the battery material in the pack have a lower recycling value, and transporting the entire pack over a long distance will definitely drive down the overall profitability very fast. And next, we can take a quick look at the technical challenges, but like we mentioned, we'll leave much of it to Kinnor to go into more details. So in short, the challenge can be broadly summarized into environmental concerns and the process route compatibilities. Environmental concerns mostly speak to the potential damage to the environment from using hazardous chemicals in recycling, and the process route capability is a general concern, as the current processes are not capable of recycling all type of batteries in a cost-effective and a sustainable manner. So lastly, I would like to quickly touch upon the economics challenges, basically as a result of several points we discussed above. So currently, the entire recycling industry as a whole is suffering from a suboptimal operating profitability. Due to the high material cost used in recycling, high environmental cost in treating the generated waste, as well as the high energy cost for some of the technologies being used right now. So in consequences, Most of the recycling operations are not considered economically viable when they are exempt on a standalone basis, which means there is not going to be self-sustainable without the synergy from upstream, downstream, or without the government subsidies. And this situation is actually worsened by the observation that the cost of acquiring the spent battery is also rising very fast, further chipping away the already narrowed margin of the profitability. So to summarize, serious problems are currently faced in recycling spent batteries from several key standpoints, and it is very important for many countries and regions to adopt more rigorous and enforceable regulatory legislations with proper incentives or subsidies, and to better clarify who is responsible in the life cycle, and basically responsibility for recycling and the responsibility for collecting the battery. And there is much room for improvement in the recycling technology to realize a cleaner operation and better economics, which will help the recycling grow as a sustainable business by itself. And together, we believe we can make this happen. And thank you all for listening. And I'll pass it to Kinnor to talk about the technical challenges and propose the solution by us to tackle them. Thank you. I'll stop sharing. This is the end, last slides.
Yeah.
Yeah.
Okay. Back to you, Kinnor.
Yeah.
I think back to Prisha, sorry.
So that's all right. I was only going to invite Kinnor to talk about the solid state recycling technology you are working on.
Yes.
So Kinnor, yes, please feel free to share your screen. Yeah.
Okay, excellent. So, can you see my screen, all of you now?
Yes, Kinnor.
Okay. So I will just go to presentation mode. Okay. Okay, so again, thank you so much. Like Brett mentioned, it's an absolute pleasure to be here today and discuss about some of the challenges and opportunities in lithium-ion battery recycling. And like my previous speakers already mentioned, there is a huge market. There is a lot of batteries that will wait to be recycled by 2025. So people are working in this space, but some of the things like Brett mentioned, there are challenges. And what we think is that there is a status quo in the recycling industry about certain types of processes which are being used for current recycling practices. But we believe that we need to disrupt that. And we need to disrupt that because we want to make sure that we create sustainable solutions. And at the same time, as Brett mentioned, we also have to make this operation profitable. We cannot rely on subsidies, and we also cannot drive the business just by claiming that it only offers sustainability. So it needs to be economically feasible as well as sustainable. So we believe there is room for disruption, and we want to challenge the status quo of the recycling practices that are available today. So like if you do a quick industry status quo and pain point analysis, of course, there are three major drivers for recycling. So there is the, yes.
Sorry to interrupt you. Is it possible to make it full screen?
Yeah, I think I just have to swap it. Is it good now?
Yes, thank you.
Yeah, sorry. My apologies for that. Yeah, so if we look into the quick industry status quo and pain point analysis, we really have three major drivers to recycle. One is definitely the environmental component, because spent EVs can be toxic and hazardous, especially because it has fluoride compounds and it has all these metals, which we don't want to expose the population to. Of course, the economic return is there because some of these elements in the batteries, they're critical materials, and there is the price of these elements, and there are issues regarding importation of these elements in certain countries. So there is economics involved. And finally, the supply chain impact, because like we all know, the lithium and cobalt, they could have like some type of supply crunch. And then what would happen to the cathode manufacturing industry or the battery industry as a whole. So recycling is definitely advantageous and it needs to be done. But some of the challenges are today, it is very high operating cost and poor economics. The pollution coming out of some of these processes, looking at wastewater treatment or emissions, they are very high. And of course, we need to make sure these processes are chemistry agnostic because there will be lots of new types of batteries. So we need to make sure that all types of spent batteries can be treated. So we believe that the LIB and the EV industry is in urgent need of a technical solution featuring both economic feasibility with strong environmental benefits. Now, one of the things that is also interesting to look at is, if we want to keep this EV revolution going, eventually we will be competing with the price of the internal combustion engine vehicle. And if you look at the graph here, you can clearly see that there will be always the fact that the EVs are expensive, but they will come down, and eventually they will maybe have to be cheaper than the ICE vehicles to make sure that we can compete. Now, for the EV price to come down, the battery is a major component of the cost, and the cathode is the most expensive part. So if you have a current cathode price, now the cathode price has to come down in the future years. So then, of course, the recycling cost has to come down as well. So if my cost of recycling is still with bad economics, then my recycled materials may not be welcome in the market because the new cathode price is so cheap. So that's why there needs to be constant innovation and disruption in the recycling space. So people are talking about new types of batteries like, no cobalt batteries. And of course, with no cobalt batteries, the recycling economics can change drastically. So that's why innovation is needed and disruption is needed in this industry. So with this in mind, XproEM has been working in this space over the last few years. And we have developed a couple of proprietary technologies. So one is the V3 physical separation process, which is essentially a unique water-free and zero waste concept process where we can recover all the components from a typical LIB pack. We can treat all the toxic fluorides in non-acidic form for recycling, and we are able to preserve the key battery materials for subsequent chemical processing. Now, once the physical separation is done, we need to go into the chemical separation. And here we want to basically recover all the critical materials from a spent cathode. And for this one, what we are trying to do is, of course, we want to do this whole process in solid state. So we don't want to melt anything so that we conserve on the energy. And we also don't want to use any harmful chemicals such as acids and caustic soda and organic solvents and so on. And because we are not melting anything, we are also using lower energy, and our CO2 footprint is also going to be low. And because we are not using any chemicals, our wastewater treatment costs will be low as well. And at the same time, we are also looking at the low value cathode materials, which are not as pricey as the NMC or LCO types. If we can directly restore the cathode and the anode to their original form without individually extracting the critical materials from these cathodes. So I want to give you a quick peek at the flow sheets, how it will look. So for the first process, which is the V3S3M process route, it's very good and highly effective for processing ternary LIB types and allows for the efficient recovery of waste battery materials into high value products. So basically, we pass the spent LIBs through our V3 process. And from the V3 process, we generate the black mass. And then from the black mass, we are able to go through the S3M chemical separation process, and we are able to bring out the lithium, nickel, and cobalt precursors. And those can be recycled.
Kinnor, I think your internet connection is not stable.
Can you hear me now? Hello?
Yep.
Yeah.
Hello?
Yeah, can you hear me now?
Yeah, you're coming through.
Okay.
Your sounds clear to
yes.
Your sounds clear to me too.
Okay, yeah. Okay, so then also, so basically the S3M process is very good for the ternary LIB types, and for the XproEM's V3 D3R process design, that is very good in recycling low value cathode materials, where the recycling of the individual materials may not be profitable, but there could be room to directly restore the cathode and anode from those spent battery packs. And for that, we are going to use the diffusion-driven doping restoration process. So if I just quickly tell you the working principle of these processes, of course, for the S3M process, what we are doing is we are basically trying to produce a black mass pellet from after physical separation, and then we subject it to carbothermic reduction. And through this carbothermic reduction process, we are basically trying to slowly reduce this black mass from its oxide forms and slowly move towards the metallic form. And this happens in layers, and that's why it's known as a shrinking core model. And basically the carbon and carbonaceous products react with the black mass and reduce it. And from there, we are able to make the metallic alloys and battery precursor materials. Now, for other batteries where we don't have the metals or fancy metals like nickel and cobalt and so on, for example, lithium ferrophosphate or LFP type of batteries, there what happens is the recycling process doesn't become very profitable for extracting the individual metals. And here what we try to do is essentially we try to restore the cathode by a heat treatment process where we can re-lithiate the cathode. So if you can see here in this little illustration, you have a LiFePO4 structure and you have a FePO4 structure. So when a good LFP battery is degraded, what happens is some of the lithium is lost, and it's in between these two structures. And we have developed a technology where we can basically put back lithium into the crystal by using a heat treatment process. And these are very useful for direct restoration of cathodes and anodes from little lower value cathodic material. So the thing is that with these solid state processes, the advantage we really have is it's a closed loop recycling process. It's environmentally friendly. And because we are not melting anything and we are not using acids and we are not treating wastewater, our operating costs come down by almost 50% than existing technologies. The capital cost is reduced by also around 30 to 60%. And we have a very good internal rate of return. And if you look, all the processes have their advantages, but with the solid state, we believe that we are also able to make the process profitable without government subsidies. And at the same time, we are able to deal with batteries of different types, including LFPs. So of course, this innovation process is continuous. We have developed these current two technologies, and we are working with partners globally to implement them and scale up. But we also have a full research and development roadmap for the next few years. So you can see all the way till 2030, we are going to work with different types of batteries for cobalt-free battery cathodes, as well as looking into new types of batteries like lithium air and lithium sulfur and so on. And finally, we want to create intellectual property and have patents in our portfolio so that we can remain competitive in this technology LIB recycling space. So with this, again, thank you so much. And it's a pleasure being here today. And we are very happy to interact with you and answer some of your questions. Thank you so much.
Thank you, Kinnor. That was very informative and very quick, I must say. You packed a lot of content in those 10 minutes. So
yeah, I tend to do that.
All right. So, so we have questions from on chat. We have questions in the Q&A box, and we have questions that we received at the time of registrations. So we can start with the Q&A box.
Sure.
We'll start with the first question. That is, it's from an anonymous attendee, and it says, what are the legislations currently applicable to recycling business in developed and developing economies? I think it was answered in Brett's presentation, but I don't think in India we have a specific and very any official guidelines yet on lithium-ion battery recycling. Is that right?
Yeah. So Brett, maybe I'll take this one because I was just having some interactions. So yeah. So but as I understand, it's being developed now as we speak. So I think it will come out very soon. And as you can see, like other than Europe, nobody really has a full-fledged national policy on this recycling thing. So Europe and China, maybe. So even the US and Canada, it's still provincial. So I think, I mean, the regulations are still sporadic, but it should be, I think this year will be when maybe India also comes out with its regulation, because they are talking with several players in India and trying to formulate a plan.
All right.
Yeah,
okay.
And I would like to add to that. I think with respect to battery recycling, It's not so much a difference between developed country or developing countries. It's more, let's say, the urgency of whether the battery is coming, that is basically ready to be recycled. Because China, we're arguing whether it's developed country, but then the urgency is mostly there because it has started having the EV back to 2015, and by this year it's already a year where a lot of the batteries are not functional. So that's why it's putting quite a bit of effort to regulate this industry. But for US and Canada especially, the EV has not been a very predominant choice of transportation yet. That's why I think the regulation has been a little behind and lagging. But like we mentioned, right? It's driven by the need of recycling, and we believe that the EV will take up very soon. So the recycling of the EV battery will likely to follow very soon too.
Okay. Right. So I would also like to tell our participants they can raise their hand if they don't want to type and they want to talk with the panelists there. Please raise your hand. I'll unmute you and you will be able to speak. Right. So next question is from Mr. Sahu. Can we limit the solid electrolyte interface to enhance lithium-ion battery life cycle?
Okay.
Yeah, this one I believe it's absolutely true. Because the solid and the electrical interaction is a fundamental mechanism for the battery to deteriorate in its capacity, and the formation of a dendrite and all the other problems are also being precipitated on the interface. So yes, it's definitely an area where a lot of efforts from research and the industry to look into. It is a good approach to take.
All right, thank you. Next we have from Mr. Sidney Lobo. How do you address the recycling of various chemistries and types of batteries? That's a very good question.
Yeah, no, it's a fantastic question. And I think this was the first thing we thought when we were getting into this, is we need to make these processes chemistry agnostic, because we want to make sure we can process. So what we have seen is that if you look at the current practices, it's difficult to process all types of chemistries, because of course you're using acids and solvents and you need to tweak it. Well, with our solid state process, we have seen that so far the types of batteries which are available in the market, we are able to handle it, but using both our processes, either D3R or S3M. And we are also now developing technologies for the futuristic batteries. So we believe the solid state process will help us make this whole thing chemistry agnostic. That is what we believe. And it has been good so far with the existing batteries in the market. Okay,
thanks, Kinnor.
Yeah. Just add to the type of the battery. The cylinder and the pouch doesn't really come to much concern when we try to implement the crushing and the grinding and the separation of the material, because we need to break down anyways. So it's just a matter of we're crushing pouches or we're crushing cylinders or we're crushing. So at that point, the difference is pretty insignificant between those.
Next is Mr. Pandey is asking, what is the current technology used in recovery of black mass?
Okay, so currently most people, after they do the physical separation and generate the black mass, most people are using either a hydrometallurgical process to extract the valuable metals out of it and process the black mass in that way. Or some people are trying to use a pyrometallurgical process where they completely melt the black mass and then they try to do some type of slag metal refining and try to extract the metals. And what we are doing is something completely different. We are trying to do the whole chemical reaction in solid state, and we are trying to recover the material. So these are broadly the three practices.
Okay. Next is from Mr. Manglik. Will it not be advisable to collect the lithium-ion battery by respective manufacturers with a nominal cost? Of course, collection and transportation may be problematic. These issues must be solved by the manufacturer himself.
Right. Yeah, Brett, go ahead. No, Brett,
Yeah,
go
we tend to agree with that,
Yeah.
and this is actually how it's regulated in a lot of countries already. And to make it more efficient, there have been systems trying to put into place to track the life cycle from the manufacturing to application to retirement. So yeah, because also the manufacturer battery knows the best, right? Like when did the manufacturer, what kind of material use. So it is being directed in such a way that the manufacturer are taking much of the responsibility. China has been a different case because just because of the large number of the fleet of EV. That's why in China the responsibility of recycling is assigned to the car manufacturer rather than the battery manufacturer. But interesting enough, the car manufacturer are now resorting to the battery manufacturer for solution and partnership in order to implement this recycling efficiently. So eventually it all route back to the car the battery manufacturers.
Yeah.
Okay. So next question is, end of life management involves battery removal, packaging for transport, recycling, and so on. Do you have indications about the cost of LFP and NMC? Do you have some indication about environmental issues like Seveso in Europe?
So if I understand what is being asked here, indication of the cost in LFP and NMC from the battery removal packaging. If we talk about the afterlife, right, not the cost of making it, then it's essentially similar, right? Because the processes are similar, the transportation costs are similar. So the overall cost for recycling LFP and NMC, they don't differ by a whole lot if we're using the same, assuming we use the same technology. So what is interesting is that LFP offer a much lower reward for recycling compared to NMC, and that is why in the world right now nobody's doing this full life recycling for LFP. Everybody's doing the repurposing because under the current technical scheme is not economically viable. So I think this is more the observation we've been making, but from the cost perspective, they're rather similar. And it just we're sorry that this issues with Civico we're not quite aware of. Maybe we'll look into it and we can have a offline chat on this in more details.
Yeah.
Thank you.
I think just to touch on the Seveso kind of note there, obviously, like all hazardous materials, the lithium-ion battery handling industry also has its associated regulations as well. Like was discussed earlier during the presentation, having on-site disposal and discharge, for example, would be kind of ideal, but that's obviously not something that's maybe as feasible. So there's currently very tight regulations around governing handling these waste batteries, because they pose a fire risk, for example, when they're stored, or explosion risk, and then how to mitigate that effectively on the pre-treatment stage when they do come into any initial pre-treatment process.
Okay, thanks, Nishit. So next question is from Mr. Rajesh. How much material by percentage of number of parts and percentage of cost can be recovered by recycling?
Yeah.
Do we have some data on?
Yeah. So I'll just give some indicative numbers, I guess. So in terms of parts, I think there's a difference between recycling or collecting. If we talk about recycling for reuse, then the parts are mostly gone, right? The cylinder, the separator, the casing, they are not no longer the original form after the processes. They're rendered to fragments and debris, which are recyclable, and we can send them to reuse of them at different applications, but they're no longer what they used to be after the process. And I think if we talk about the chemistry, then the cathode and the anode, they're mostly what they used to be, but we still need to do the work to restore its functionality. So I think that's so number of the parts, I would say very little. Most of them, they're no longer in their original form. But the cost, it's interesting concept, because now we don't look at the battery as a battery itself, because now we look at it as from recycling material. So we'll see that from I think Nishit's presentation, cathode stands for 40% of the total value. Now we talk about value rather than cost, right? So that's the most significant portion of it. And also there's good value from the anode material, and as well as some of the aluminum and the copper foil being shredded. So we believe there about 50% of the material has a good recyclable value, and the rest they just don't beat the cost, because you'll be cheaper to acquire them anew rather than going through the process. So we'll say about 40, 50, 60% of the material that has a recyclable value.
I think there was another question that we got at the time of registration around actually the viability of lithium-ion recycling, because now the batteries are going nickel-free, cobalt-free, that are supposed to be the expensive materials comparatively, and the LFP batteries are gaining ground. So there were questions, I think a couple of people asked questions around that given that we are going to see more and more LFP batteries, how much lithium-ion battery recycling, how much is it going to be a profitable business, just from the economics point of view?
Yeah. So okay. I think, Brett, you want to take it? Go ahead.
Yeah. So this one is a good topic, because we've been discussing this with a lot of partners and and agencies as well. Yes, it is definitely a very alarming trend from recycling perspective, and the cost, the value, recyclable value, is driven down very fast when we switch out to this lower cost material. So this is essentially giving us the challenges, right? How are we going to remain profitable when the top line of the business is shrinking more and more? So this is essentially why we are resorting to the cathode restoration process, because it is a lower cost operation, because we don't use much chemicals and additives to render the material recyclable. So the solutions is that the technology had to evolve, because the current hydrometallurgy is not going to work, because it's just too expensive for any of this new battery. And creativity, right? So we need to come up with new technical solutions, new framework, right? Outside box, rather than what people have been doing last 20 years. It got to be something new, right? The old traditional method are not going to work with the new battery.
Yeah, good. I think it's a good presentation and good exposure. But I was just wondering, isn't too early to go into this business, because what I say is a war of batteries actually going on. You have aluminum battery, you have hydrogen going on, and you have a number of other things going on. So how do you see this whole thing going forward in 5 years down the line? Who will be coming as a main source of EV energy source? I'm not sure about that.
Right.
Yeah.
So
again, very good question.
Yeah, very good question, Mr. Khare. And I think what I will say is, if you look at large countries like India or China, there will be combination of everything. You cannot just bet on one particular source for fueling the clean future. So if you think just for India now, like the research we have been doing, sure, in India, we don't have yet the 4-wheeler EV thing coming on the roads. But if you go from the 2-wheeler and 3-wheeler perspective, it's already generating a lot of batteries, which are going to come to their end of life.
But 3-wheelers generally have lead acid, probably what I understand from them.
Sorry, what was that? 3-wheelers?
3-wheelers have this lead acid batteries, not.
Oh, it's changing now. Now they are going. It's changing, okay. And it's going to come to end of life very soon. So we are talking about 2021, maybe 2023. They will need recycling. So I think even for a market like India, I think it's a good time we are discussing these topics. And
hey, this is a good thing that we have to be into this whole thing. This is the right time to be in, actually.
right.
And I'd just like to point out that whether hydrogen cell battery or lithium battery, I think it's not a simple yes and no. I think it's a very complicated analysis you had to take in order to find out which one is in the right battery.
Yeah, it'll take some time to settle down. It'll take some time to settle down.
Because for example, lithium battery perform poorly under cold conditions so far, and the fuel cell battery does perform better. But then the cost of the hydrogen cell just hasn't come down yet. It's not in the commercial scale yet.
But then aluminum ion air batteries are doing, they're at advanced stage of manufacturing rather.
Yeah,
but that's not another 10 years.
Yeah,
sure.
maybe 10 years.
So we are dealing with a rolling task right now. We're dealing with, but from our perspective, we're recyclers. We just need to tackle down the battery with the right approach and the right chemistry. Right. So I think recycling is never too early. It's a matter of which one we're focusing on.
Certainly.
Hitesh, do you want to ask your question?
Thanks. It's a very wonderful workshop and good knowledge insights. So I would just like to understand the economics, what mentioned, the internal rate of return of more than 35%. But from the perspective of the total techno-commercial viability point of view, how should one go about the size of the plant? What is the minimum capacity that one should look for? So that also has the total investments needs to be looked at, and the future plans needs to be done over a 5-year, 10-year horizon. So how should one go about it?
Yeah. So Nishit, maybe you can answer. Yeah.
Yes, I was going to say, like all technologies, obviously, going with a larger facility offers you that economy of scale. And obviously you could gain some good efficiencies when you get a larger size facility. What we're seeing with our technology, that number that you saw in the presentation, is based on a module that's over 10,000 tons a year of processed black mass amount or spent batteries amount. So when you think of it that way, anything from 5 to 10,000 tons and more already starts to confer very strong economic benefits. And then obviously as you scale up and go bigger, you get even more to gain by that economy of scale.
So just to understand, is the plant has already been set up to that capacity and these economics are working out is the result of actual numbers, or is it under process that you are trying to set up?
So this is underway as we speak. For our technology, we've been able to successfully validate and prove that this works at an industrial scale, not at that level yet. That's the state we're at right now, looking to align all our resources to be able to get there.
Okay. Thank you. All the best.
Thank you, Hitesh. So we have more questions. I would again say you can raise your hand and ask your question directly. Otherwise, we'll continue taking questions from the Q&A box. So one question from Mr. Saurabh Chawla. Please advise the business models suitable for Indian ecosystem with regards to second life lithium-ion batteries and then recycling of end-of-use batteries.
Yeah. So Brett, would you like to take that one?
Within the Indian ecosystem, specifically, I mean, if it were from a recycling perspective, I think we would partnership with, first of all, agencies that are authorized or designated for collecting the battery. Because that's, as we mentioned, it's a challenge in a lot of countries. So knowing the local system and working with them is the first priority. And secondly is to find out the chemistry and who are the manufacturer and what can we sell the recycled material to, and we'll likely form a alliance with them to basically have a offtake partners for our material. So essentially, it's a collision. It's an alliance, and it's a partnership between upstream and downstream, ideally to formulate this closed loop concept. And I think this probably is what we'll be looking for in other countries too. So it's likely to be a good model for India as well.
Yeah, so just to add to Brett, in terms of the business model, what we are trying to do is we always try to work with local partners who have a good idea, the lay of the land, and they are also having a network for collection and maybe also producing the black mass. And then we try to partner with them, and then we bring in the technology because we have the proprietary technologies which are pending and patented. And then we are trying to develop jointly in every local jurisdiction in that way.
Okay. We'll take one. We will be a little mindful of time now because I think only 4 or 5 minutes left.
Yeah.
So I can carry on with the session for another 15 minutes. So if the panelists' schedule allows, we can stretch it by next 10 or 15 minutes to take up the questions.
No problem.
Sure.
We are very happy to
All right.
interact. Yeah.
Okay.
And also we provided the email. So if we cannot finish, most welcome to email us, and we are very happy to discuss.
Sure. So I think Mr. Rahul wants to. Rahul, do you want to ask a question? Okay, you can unmute yourself now.
Thank you, Rakshi. Hi, gentlemen. My question was basically around the patent side. Is this a process patent that we are looking at, or is this a design patent that you're looking at?
Sorry, Rahul, somehow I couldn't hear you because of the echo.
Am I audible now?
Yeah, better.
All right. What I was keen to essentially understand is the patent that you're looking at. Is this a process patent or is it a design patent?
Okay, so unfortunately, Rahul, you broke up again. I couldn't hear you.
So Kinnor, I think they're asking whether it's a process patent or design patent for the patent you speak about.
Okay, so basically, you see, Rahul, we are trying to create a portfolio of patents. So we are trying to have some design patents, some process patents, and some overall patents on the concept. So we have been filing constantly, and we are trying to get the global protection. And that's how we are moving forward with a full IP portfolio and strategy.
Yeah, so in the North American, we have a utility patent, which is essentially the design patent. In Asian, some Asian countries, we filed what they call, I think they call design patents, which is same thing as utility patent in North America. So yeah, I think we're following the more rigorous approach.
Yeah.
All right, thank you.
There was one question around from a safety perspective, what are the major things that must be considered?
Yeah, absolutely. So some of the things, firstly, when you are doing the battery collection and handling, I think that time the safe discharge is very, very important, right? Before you can do anything further. Then, of course, these batteries have like fluoride-based electrolytes and things like that. So fluorides are very dangerous. I mean, they are very corrosive and very dangerous. So that has to be protected. When you are doing the crushing and grinding, there will be a lot of dust and fine particulates coming out. And there could be fine particulates of these critical metals as well, which are not very friendly to the human body. So that has to be protected as well. And then during the entire recycling process, at least for our technologies, of course, we want to make sure that the emissions are limited. So we need to have very good emission control systems, and also try to make it closed loop so that any CO2 that can emit, we're trying to use it in some other process in our flow sheet, so that it's pretty much a zero emissions type of process. So these are some of the safety measures we have to take. Apart from that, LIBs while transporting, there could be fire hazards. So I think those also have to be taken into account while transportation and the logistics. Okay. So Brett, maybe anything else I missed you can add?
No, that's pretty comprehensive.
Yeah. Okay, perfect.
Okay, we have one question from Mr. Satpathy from BHEL. So he says that BHEL has set up a pilot scale space grade lithium-ion cell manufacturing facility, and they generate waste, of course. So they are interested to recycle this, though the amount of waste generated is very less, but they're interested to, of course, recycle whatever waste they are generating. So any suggestions there, or is that something XproEM can help with? I think Mr. Satpathy is in the session?
Yeah, I am there.
Yeah.
Yeah, I also want to know, Professor Chattopadhyay, that what is the tier level of this technology? What kind of level you are?
Yeah, so I think we are around, I would say 8-ish, and we are going to 9-ish this year. So we are just in the process of setting up some demonstration scale facilities in Asia, as well as we are partnering with some Indian players in India. So you will hear some good news about the plant being set up very, very soon, within a year or so.
That is great. That's great. Thank you very much.
Yeah.
Mr. Ranil, would you like to ask a question now?
Yes, Mr. Priyankshi. I have just one question to Mr. Kinnor, sir. Sorry, I have joined late. So I just want to know, in India, you have a facility for recycling. Can you share with us the recycling process video so that we can get the more knowledge about that?
Yeah, so Mr. Kumar, we don't have the video yet. So we are working with a local partner to set it up. But of course, like I said, you will hear some positive news very soon about setting it up. And we are very happy to share and talk about it once we have it set.
Thank you, Mr. Kinnor. We will keep in touch with you for getting a good news in future.
Absolutely.
So thank you very much. Please.
Thank you, Mr. Kumar. Thank you so much. Yeah.
Okay. I'm just Rahul. Okay, just you can unmute.
Hi, it's me again, Brett.
Yeah.
All right. So, Priyankshi,
Okay.
for the
More questions before we close this.
Just the last question. Sorry. Yes. Brett, Mr. Kuno,
yeah,
we are already connected on LinkedIn.
Yeah.
I did send you a couple of messages around because we, on a parallel scale, have been doing e-waste recycling since around more than a decade now.
Yeah.
And would be most interested essentially to connect and take this forward.
Sure.
I have a colleague of mine who's based out of Toronto.
Okay.
I have already shared your connect with him, right?
Yeah.
So he would most probably reach out to you. Prakshi, just for Mr. Chattopadhyay from Bhel, so we, as in, if there is a possibility, I can drop you my mail ID. We can absolutely assist with Mr. Chattopadhyay's request for the recycling and stuff.
That will be great, sir.
Thank you, sir.
Thank you very much.
Rahul, you can share on chat. You can share, yes.
Yeah. So Rahul, we will definitely get back to you. I think I was a little bit tied up a couple of days, so maybe didn't check my messages properly, but we'll definitely come back to you.
Thank you.
Okay, thank you. I think we'll take one last question. It's from Mr. Rangaswamy. What will be the likely cost addition of the recovered metals compared to the virgin metals from the ore? How much costlier is the recovered material likely to be? And would it be attractive enough for the battery maker to source, unless there's a government mandate to make it compulsory to source from the recycled materials?
Yeah,
right. So
I'll happily take this one.
Nishit, please.
Yeah. So I think that's a very good point, and that's kind of the pertinent point when you're talking about making this a very sustainable technology, not only environmentally but also economically, because this is a very key point. So I think we agree, and I've found that it is indeed competitive, and not only competitive, it's actually cheaper than sourcing some of these materials in their raw mined form, which then allows us to offer that benefit, like Kinnor mentioned during the presentation, even without the need for any subsidy or any kind of reduction in cost from any kind of incentive. The process itself allows for recovery of these metals at a lower cost than it is to freshly source, which means that it does indeed allow us to be competitive and source them, or allow for sourcing of these raw materials in the market at a more efficient and low cost way.
Yeah. And I'll just add to Nishit that in certain countries, these materials are not available. So you have to import them at very high prices. So in those countries, I think the recycling will be mandated. So they will try to create a local ecosystem, a local economy, so that you don't have to blindly rely on, sources from other countries. And then, with certain geopolitical activities, you are not being able to resource those materials. So I think that's why recycling will also come into play from that angle.
Right. So I think, Kinnor, if you could just share your email address on chat, please, if there are any other questions. If somebody missed to note it down earlier, they can note it down now.
Yeah, I will just...
I have just one last question. After your recycling, what kind of purity level you achieve compared to the raw material earlier used?
Oh, it's almost similar. It's almost similar with, I would say the precursor materials would be like maybe, 95, 96% of the, if it was mined. So it's still battery grade. So there is no problem in putting it back into the market.
Thank you.
Okay. I think okay. So thank you. Yes. Thank you so much for this very informative. Shubham Mishra. Okay, Shubham, if you can take, I think raise hand as well. Okay. And then we'll wrap it up. Please go ahead. Shubham, you can unmute yourself, please.
Oh, yeah, sorry. Yeah, hello, everyone. I had a question regarding the recovered rate, which is achievable in different chemistries that are available in the market right now. Is there any variance, or are we able to collect almost similar percentage of material from all the different chemistries that are available?
So for most of the chemistries, we are getting a very good recovery rate, like in the upper 90s. So I would say that there is variance, but the variance is still above the threshold where we are able to sell it back, or it will be accepted back. So the variance is there, but it's not anything below any accepted level. It's always above the accepted standards.
If there is any variance, then what is the highest recovery rate for a particular chemistry, and what is the lowest rate in which you are getting from a particular chemistry?
Yeah, so with time we have tweaked the process, and now we can get for most of these materials, we can get into, like, I think the lowest would be 91, 92, and the highest is like 95, 96. So that's kind of the variance in the process.
Yes. What I mean to ask is, like, 95 is for which type of chemistry, and 91 and 90 is for which type of chemistry?
So see that's okay. So this is a very good question. So what happens is, when we are receiving the black mass, it also depends on the quality of that black mass, like how much of it is mixed with graphite and so on. So I think the variance is mostly coming for that. So we still are not yet able to pinpoint like exactly the effect of the chemistry on this recovery rate. But because all the recovery rates are above the threshold, we didn't pay much attention to that aspect because everything is working.
Okay. That answers. Thank you.
My pleasure.
Okay. Thank you so much. I would like to thank all the attendees for making the session so interactive with your questions, and of course all our panelists for sharing from their experience and the new technology they're working on. We look forward to more such sessions going forward, and everybody have a very nice rest of the evening and stay safe. Thank you so much.
Thank you so much. Thank you for having us. Bye-bye. Bye-bye.